In today's lesson, we're going to look at series. And the first problem on your note sheet is a little problem about an amphitheater. And it says, suppose a section of an amphitheater can seat 18 people in the first row, and each row can seat 4 more people than the previous row. Well, what we looked at yesterday with sequences could be used to do this problem. We have 18 as our first term. Our next term would be 4 more, which would be 22. 4 more than that would be 26. And we could keep going and come up with a sequence of numbers that keeps adding 4 onto the previous term. So once you have a sequence like this, you got a bunch of numbers. What we're going to look at with series is taking a sequence and then finding the total. So the next part of this problem says find the number of people who could sit in the first 5 rows. Well, the first 5 rows here would be 18 we know is our first row, or ace of 1. This would be our second row, or ace of 2, a of 3, a of 4, and a of 5. So a series, what it does is it takes your numbers in a sequence, and if we want to find the total, or the people that could sit in these first 5 rows, we would find the sum of these 5 numbers. So we would add them up. So we would be trying to find what is the sum of the first 5 rows. So if we add all those numbers together, then we would have the total. And in this one, that comes out to be 130 people if you add those up. So a series is a sum of the numbers in a sequence. All right. Let's do a little story here. Back in the late 1700s, there was this guy named Carl Friedrich Gauss, and he was a student in a small German school house. Gauss was kind of a troublemaker, and the teacher kind of got fed up with him, and as a punishment, he made Gauss sit in a corner and add up the first 100 integers or whole numbers with the thought that this would take him a long time and be a tedious task as kind of a punishment. But Gauss ended up finishing this problem within seconds, so it really didn't end up being a punishment at all. Now, Gauss, this guy turned out to be a very smart scientist and mathematician. He saw kind of a quicker way than adding up all the numbers one by one, kind of like we did in the last problem. What he saw was a kind of a pattern. He saw if we take these first 100 numbers, starting at 1 all the way up to 100, he saw kind of a pattern here. He said, well, if I take the first and the last number and add that together, that's going to equal 101. Same thing if I take the next 2 numbers and add those together. It also equals 101. And if you keep doing that, they all equal 101. So then he said, well, how many pairs of numbers would I have between 1 and 100? So he said, well, if I got 100 numbers and I divide that by 2, that would give me 50 pairs of numbers. So if I got 50 pairs of numbers that all add up to 101, he said that you could find the sum of these first 100 terms by doing 100 divided by 2, adding up the first and last number. So you got 50 pairs of numbers, all adding up to 101, and if you multiply that out, he got a total of 5,050 relatively quickly without having to add up all the numbers. So he did it by doing a pattern, and then obviously his teacher probably wasn't too happy with him, but he came up with a creative way of doing this. So on that first problem there on your note sheet, that's a quick way of being able to add up the first 100 positive integers, is to use that little pattern. And that pattern we're actually going to use as a formula here. So in your note sheet, you have this formula right there. That's the formula Gauss came up with, is that if you want to find the sum of a sequence of n number of terms, you can do it by adding the first and last integer times the number of pairs. So in this formula, n is your number of terms. A sub 1 would be your first term. A sub n would be your last term. So you can use that formula anytime to find the sum of a sequence. Now, there's another formula on this one next to it, another sum formula. This one's a little bit different. This would be a formula you'd use if you did not know what the last term in the sequence would be. So this one instead uses a lot of the same type of things we did in this other formula, except it uses the common difference. So remember D from yesterday, that means the common difference. How much is it increasing by each time? So these two formulas can be used to solve some of these types of problems. Let's try one out. On number 2, on your note sheet says, Aiden did push-ups every day in March. He started on March 1st and increased the number of push-ups done each day by 1. He did a total of 1,085 push-ups for the month. How many push-ups did Aiden do on March 1st? Okay, so we want to find something out here. Let's look at everything in the problem and see what we have. First, they said he did a total of 1,085. That total would be all the push-ups for the whole month. That would be our sum. So our sum of however many days is going to add up to 1,085. Another thing that they tell us in the problem would be that the difference. How much did he increase by each day? What's our common difference here? And our common difference, what he's increasing by is they did 1 more push-up each day. Okay, so they increased each day by 1. So our D in this problem is going to be 1. There's also kind of one more piece of information that not specifically said, but he said he did the push-ups for the whole month. So for March, in the month of March, we have a total of 31 days. So the number of days is going to be 31 in this problem. So now we want to take the information and decide which equation here would be best to use. With the information we have, we don't know how many push-ups this Aiden guy did on the last day. So we can't use this formula. We want to use the first one here. So we want to put our information into that equation and then solve for how many he did on the first day. So he started with 1,085. That's our sum. Our number of terms is 31. Divided by 2, the formula is divided by 2, times 2 times how many Aiden did on the first day. That we don't know. We're going to keep that in our formula as a sub 1, plus the number of terms minus 1, so 31 minus 1, times the common difference. Each day he's doing 1 push-up more. So if we go through and simplify and do a little solving here, we can come up with how many Aiden did on the first day. So let's start out. Let's simplify, use order of operations. We should be able to do this. So we got 1,085. We could do a little division here. 31 divided by 2 is going to be 15.5 or 15 and a half. We got to make sure we get parentheses simplified here. That would be 30. And then 30 times the 1 would be just be 30. All right, so now we got to keep simplifying here. We could distribute this 15.5. That would be one way we could do it. All right, another way would be to get rid of that number. It's being multiplied to this parenthesis, so we could divide each side by 15.5 would be another way we could do it. Let's try that out. So if we divide 1,085 by 15.5, we get 70. Now it should be pretty simple from here. Subtract 30, divide by 2, and it looks like on the first day, Aiden did 20 push-ups. So the answer would be 20. All right, for tomorrow, I want you to see if you can try out number 3. So let's try this problem. Use one of those 2 formulas, see if you can do this third problem. And also try number 4. This is very similar, number 4, to number 1. Slightly different in that it's just the odd integers, but I want to see what you can come up with for that one. All right, let's go to the back of your note sheet. Number 5 says find the first 3 terms of an arithmetic sequence in which the first term is negative 16, the last term is 33, and the sum of all the terms is 68. Okay, so we got the first one, we got the last one, we got the sum. We want to try to figure out what it's going to be. So this one, since we know first and last term, this might be a better equation to use in this one. So let's plug in what we know here. Our sum would be 68. That's going to plug in for there. 33 is our last term. We can put that in there. It's negative 16 is that. The one thing we don't know is n. So we can solve now for, or should be able to solve for n and figure out the number of terms. So doing that, we have, let's see, sum is 68. N we're not sure of. First term, negative 16. Last term, 33. So doing a little solving, if we add the parentheses together, we're going to get a total of 17. Multiply, dividing, we could do a couple different things here. We could divide by 17, or we got this divided by 2 stuff. So one thing we could do would be to times both sides by 2. That would eliminate that 2. So you got 17n equals 68 times 2 is 136. Divide by 17. And we find out the number of terms that were added up was 8. Now, does that let us get to our answer? Not quite yet. Not quite yet. We need to know how much is this increasing by each time. Well, we now know another piece of information right here, this n, that n is 8. So now we can use this other formula to try to find out what's the difference. What's our common difference here? So using this other formula and plugging in some of the same numbers, we could put 68 here. We could put negative 16 in for there. We now know n, and we could substitute that in for here and here, and we could find out our common difference. So we got 68 equals 8 over 2. 2 times our first number is negative 16 plus 8 minus 1. What we don't know is what is it increasing by each time. What's the difference? So we got some simplifying to do here. 8 divided by 2 is 4. 2 times negative 16 is negative 32. Our parentheses equals 7. Let's divide by 4 here. And if we divide that by 4, we're going to get 17. Add 32 to both sides, and we're going to get 49. Finally, divide by 7, and our common difference is 7. So now we can, if we know the common difference, we should be able to find the first 3 terms. So if negative 16 is our first term, and our difference is 7, that means we're adding 7 each time. If we add 7 to negative 16, our next number is negative 9. Add 7 onto that, and our next number is negative 2. So those would be the first 3 terms in the sequence. All right, this next part has a new notation. This is called the summation symbol. And what it means is that we're going to be adding together a bunch of things. So summation means you are going to be adding together the terms from this starting value for n to this ending value using whatever equation that's listed here. So in this one, they want us to find the sum by going through. So on this one, that would mean if we plug in 1, our first term would be 3. 3 times 1 is 3. If we plug 2, our next number in for n, 3 times 2 would be 6. And we'd keep going all the way till we got to 10. So if we plugged in 3, 3 times 3 is 9. 4 times 3 is 12. 5 times 3 is 15. And we could keep going. 6 times 3 is 18. 7 times 3 is 21. 24. 27. Finally, we get to our last term. If we plug 10 in for n, 10 times 3 is 30. So they want us to add up all these numbers. Well, you could sit and go on your calculator and do that. It's kind of a lot of work, and it would be even worse had this said maybe find the sum for the first 100 numbers. Then you'd really have to do this for a long time. So is there a quicker way? Yeah, the quicker way is, again, using some of our formulas up here. So this would be a good one to use this formula. If you want to find this faster, use that summation formula. So the sum of our first 10 numbers would be found by doing the number of terms. That's going to be n, so 10 terms, 10 over 2. The first term, by putting 1 in, if you do 1 here, 3 times 1 is 3, so that's our first term. If you put our last term in, 3 times 10 is 30, so that's our last term. Now we could use that little formula from that problem from Gauss to do this one. So 10 divided by 2 is 5. 3 plus 30 is 33. If you do 33 times 5, you can get the answer a lot quicker. It's 165. Okay. All right. We'll take a look at some more of those tomorrow. See if you can try and figure out number 7 for tomorrow.